Okay, welcome back, everybody. Hope you're all rested and ready for the final stretch. Let's just remember where we are and where we're going. We are going to start today into our section on challenges. Field of evolutionary robotics hasn't been around that long. It's only been around for about 20 years. There's a lot of open challenges to which no one has a good question, so we're going to spend the next couple weeks looking at some of these challenges, and who knows, maybe someday one of you will come up with a good answer to these challenges. We'll start today with modularity. I think we'll probably get all the way through this lecture today. We might start in on the first slide or two of lecture 14. I apologize, I haven't put up lecture 14 yet, but we will start in on lecture 14 in earnest next time. Okay, so let's see, where else are we? Undergraduates, you hopefully finished assignment 8, the quadruped, which is a lot of steps, but the idea of introducing the quadruped this late in the game is to use that minimal scissor bot to get you comfortable with all the building blocks that make up a robot: objects, joints, sensors, motors, neurons, and synapses. Now you're working with a robot that has lots more of all of those building blocks, right? That's assignment 8. Okay, so assignment 9, we're going to switch back now to working our way through a series of increasingly powerful optimization methods. We started with the serial hill climber. One parent produces one child. If the child is better than the parent survives. If the child is worse than the parent survives. That's the serial hill climber. Then we switch to the parallel hill climber, where now you have a population of parents. Each parent produces one child, and we play the same game, but in parallel. In assignment 9, we're now going to introduce the most common evolutionary algorithm that's out there, which is the genetic algorithm. And the genetic algorithm is, again, not too far removed from the parallel hill climber, but it has some advantages over the parallel hill climber, which I'll ask you to think about now. So here's the pseudocode of what you're going to be implementing in assignment 9. We're going to start with, again, a population of parents. So I'll just represent this as an array, and you can imagine that in each element in this array, there's a robot. We're going to then create a second population. At the beginning, this population is empty. We're going to fill this with children produced by the parents. So we're going to start in step A to create and evaluate all of the parents, and then we're going to repeat a number of generations like before. So step C, create an empty child population. First thing we're going to do is copy the best parent into the first slot of the child population. So let's imagine that P0 here happened to have the best fitness in the population. We take that individual and copy it into this slot here. This is known as elitism, so we're making sure that the elite always survives from one population to the next, from one generation to the next. We'll see why in a moment. We now have n-1 empty slots in the child population. So we go back to the parent population. We pick 2 parents at random. We check to see which of those 2 parents has the higher fitness. Whichever one has the higher fitness, let's say it's this one, we produce a copy of this individual, and then we mutate it and place the mutant into this slot here, and rinse and repeat. Pick another 2 parents at random. The winner is allowed to produce an offspring, and we keep going until we fill every slot in the population. Once we're done, we delete this population and rename this as the parent population and repeat for the next generation, and so on and so forth. Do you have a question? No?
Do you remove previously randomly chosen parents? So like if you randomly chose P1 and P5,
Yep.
do you immediately remove P1 and P5 from the random pool?
That is a good question. So if we picked P1 and P5, let's say P1 produced an offspring. The next time we pick parents again, P1 or P5 may be selected again. Why do we do that? Why do we not remove P1 and P5 from consideration when we're picking the next pair of individuals?
P1 would be like the second best in the population peaking during
possibly.
If you remove 2 every time you pick one, you run out of room in the child population.
We'll also run out of room, that's true. Think about the best individual in the population. So in my little cartoon example here, P2 is the best, and we made a copy of it. We didn't mutate it. We made sure that it's preserved into the next population. If we're picking individuals at random and we keep allowing repeats, which individual up here is going to produce the most offspring into the new population? Would be P2, right? So if P2 has the highest fitness of all the parents, and we're picking pairs at random, whenever P2 is one of the 2 that's chosen, it's always going to win, right? So if it gets chosen multiple times, it may not, but it may, it's going to produce quite a few offspring, right? So now we can see that the genetic algorithm is a better approximation of biological evolution than the parallel hill climber was, because in the parallel hill climber, everyone is allowed to produce exactly 1 offspring. The main difference between the parallel hill climber and the genetic algorithm is now the more fit you are relative to all the other individuals in the population, the more children you're likely to produce. But it's probabilistic, right? Because we're picking pairs at random. We may actually, in this cartoon example here, never pick P2. Maybe the only thing P2 does is survive into the next population. But the probability of that is relatively low. Okay. Why do we keep a copy of P2? Why step D here?
Because it's the best, and at random you could theoretically not have P2 at all.
Exactly. So if we didn't copy the best into the next generation, it's possible that in these selections we never actually picked P2 for any of these pairwise competitions, and P2, which was formerly the best in the population, dies out. And the best fitness in the population at the next generation may actually be lower than it was in the previous generation. So by adding step D here, we're just sort of assuring that we keep our high water mark. So whatever was the best, we at least keep that. There may be a new mutant that evolves that is better than P2. So fitness can still go up over time, but it's never going to go down. Okay, that's the genetic algorithm. Any questions about that? There is one difference between my genetic algorithm and most other genetic algorithms that you might read about online or in the literature, which is there's no recombination here. Why have I not included recombination? Why not pick 2 parents and take parts of the genetic material from both parents and put them into one of the children? It's not necessarily complicated. It would be a few lines of code to write it to implement it.
As the generations go on, the new children will be more and more similar. You might end up with like another P2.
That's true. It might be that actually decreases diversity in the population. Actually, leading theories say that sex evolved in nature to do the opposite, which is to increase diversity, mix and match material from different organisms. So one reason to actually put it in is to increase diversity. One of the things you'll notice as you're implementing assignment 9 here is that you start to see diversity go down. You'll start to get individuals that are more and more similar to one another, which is something we'll tackle a little bit later, but not in assignment 9. Why is recombination not in here? Think about what is the genome here? What is actually being encoded? If we actually were to genetically recombine genetic material, what is this genetic material? We're mutating and we could possibly recombine genetic material from robots, but what aspect of the 2 robots that are chosen might we recombine? What's encoded in the genome? The synaptic weights, right? So we have we pick two parents at random, we're actually choosing two neural networks with synaptic weights. We would be cutting those neural networks into halves, perhaps, and taking two half neural networks and plugging them together. What's the chance that taking two halves of a neural network and plugging them together is going to produce a new neural network that does better than either of the two original neural networks? Pretty low, right? So if I grab one of your Windows machines and I grab one of your Mac machines and I cut them in half and glue them together, what's the chance I'm going to have a third laptop that does better than the either original, right? Pretty darn low. That's probably the case here as well, which turns out to be an open problem in neural network theory called the competing conventions problem. So Windows machines and Mac machines have two different conventions inside, two different operating systems. If I plug them together, we've got competing conventions. They don't speak the same language. It's not going to work. Same thing happens with neural networks. And in lecture 15, we're going to look at a pair of optimization algorithms called NEAT and hyperNEAT. And these algorithms were designed to allow you to sexually recombine two neural networks and produce a third neural network that in some cases is better than either of the originals. It's a little bit tricky, so we're going to spend some time going through that, but that's what this algorithm was designed to try and solve, this open challenge of the competing conventions problem. Okay, so for our purposes, we're going to just sidestep that problem for a moment and just not have recombination in here. We're just going to mutate parents into new children. Any questions about assignment 9 or any of the assignments so far? No? Okay. So let's hop back to lecture. We're going to work our way through lecture 13 today on modularity. And, one other thing I wanted to mention about the schedule. I've been hosting office hours on Twitch, and in between people asking questions, I've been coding up yet some other optimization algorithms. So when you finish with the genetic algorithm, later in the semester, if you want to replace the genetic algorithm with something that's even more high-powered, check out the video from March 6th. I talk about coding up a steady-state evolutionary algorithm. And yesterday, I talked about coding up multi-objective optimization. Both of these are a little bit more high-powered than the genetic algorithm. But they're just there as optional algorithms if you want to try and tackle them. Okay, so why is modularity a challenge? And what do we mean by modularity? Well, we've mentioned this a few times in the course so far. Modularity is not just an important concept in robotics, but in a lot of domains of science and engineering, and especially in computer science. There's lots of different formal definitions of modularity, but we're going to use sort of just an intuitive one today, which is that we have some system, which could be a neural network, it could be a bunch of code, and in that there seem to be these modules, and a module is something in which there is a lot of interconnectivity within that module, and a lot of connectivity within another module, but few or little connections between modules. That's, for the moment, what we're going to mean about that. I'll show you an example in a moment taken from computer programming. Why are we talking about modularity? Well, one of the reasons why is any intelligent agent should be able to break problems down into smaller and simpler subproblems, so we can treat those subproblems as modules. We've spent a fair bit of time in this course talking about the various building blocks of intelligence. We talked about self, non-self discrimination. This is me, this is all non-self. We've talked about affordances. So when I look out on the world, I see things and I classify those things based not just on their geometry, but based on how I might interact with them. That's affordances. What else have we talked about? What are some of the other building blocks of intelligence we've looked at so far? Memory, right? Got to remember all these. What are we missing? Active categorical perception. So I reach out in the world and literally grab objects to understand differences and similarities between objects. I'm missing one. I mentioned affordances. Memory, affordances, self, non-self discrimination, active categorical perception, and so thank you, and selective attention, right? Hopefully for the moment you're paying attention to me and you're somewhat ignoring your phone even though it might be buzzing at you and trying to grab your attention. You're selectively deciding what you want to pay attention to. Another important building block of intelligence, again, is when you're confronted with a complex problem, you can notice that there's some structure in the problem, break it down into independent pieces, and tackle those pieces in turn. Actually, in the final project, we're assessing your intelligence and how well you can take your final project and break it down into bite-sized, independent, weekly projects, right? It's a good hallmark of intelligence, the ability to do that. Later in the lecture today, we're going to see a robot that was evolved to try and break its problem that was posed to it by the investigators down into smaller bite-sized chunks. So just to situate why we're talking about modularity, it is yet another one of these building blocks of intelligence. Okay, so a module, for example, in object-oriented programming is the object, right? We try and encapsulate inside an object variables and functions, and a lot of those variables and functions are hidden from view from other objects, right? So we try and hide stuff and simplify the communication between these objects. Okay, why do this? Well, part of the reason why is once you start to break things down into modules and you want to try and improve your system, you can make changes to the guts of one module without breaking the overall functionality of the system. If you have a system that's non-modular, in which everything is connected to everything else, you've got a big spider web, you make one change over here, and that change is going to propagate throughout the entire system. Okay. So how do we actually do that? Well, for example, I think I showed this example last time. Bullet used to be the physics engine we used last year. We could create a class and class instances or objects where we have generic shapes in our physics engine. And for every shape, we want to create them, delete them, and draw them. Once we create the module called shape, we can compose that module into larger modules like robot, right? So modularity is also somewhat related to hierarchy. Once we break things down into small pieces, we can then hierarchically arrange them into larger and larger pieces. Okay. All of these things allow us to create increasingly complex code. If you've ever tried to write a large program in which you don't use object-oriented methods, things get pretty difficult pretty quickly, right? Your code starts to be all interconnected. It gets hard to expand the functionality of your system. So similarly, we'd like to evolve a robot that breaks its problems down into independent subproblems so that our robot can continuously increase its performance and expand the things it can do over time. If it can't do that, like writing non-object-oriented code, it's going to be hard for the robot to expand its capabilities if everything it does affects everything else. Okay. We've actually mentioned, or I've mentioned as we've gone along here, two different kinds of modularity. Structural modularity. Let me see if I can bring up an example of this here. Actually, let's just do this at the board. Structural modularity is the idea that we're going to actually create structurally independent parts of a neural network. Let's imagine that we have a neural network that's made up of 4 neurons. If we were to connect every neuron to every other neuron, how many synapses would we have? 1, it's going to be more than 6. 10, right? So everything is connected to everything else. How did you get 10?
Well, if you connect each one to each other, there's 6, and then if you connect each one to itself, it's another 4.
Okay. What's the equation for this? That's right. If we have n neurons, how do we express it as a function of n?
The summation from I equals 0 to n.
Yeah. Let's say we were to write this as a matrix, an n by n matrix, like you do in the programming assignments. So every element in the matrix Every element ij encodes the synaptic weight that connects neuron I to neuron j. If we have a neural network with n neurons, what's the size of that matrix?
Wouldn't it be n times n minus 1 plus n over 2?
If we're only taking the upper triangle, right? But we're actually interested in not just synapse ij, but also synapse ji. It's important. So we're getting close. We have n neurons. We're going to encode the synapse in that fully connected neural network with n neurons in a bi matrix. How many synapses do we have? Not quite.
16.
What's that? 4 by 4, right? For the 4. So if it's n, it's n squared, right? We have an n times n matrix, and every element in that encodes information about one of these synapses. So if we have a structurally non-modular network, everything is connected to everything else. As we start to build a more complex robot, it's going to need more sensors and more motors and more neurons. So as the number of neurons goes up, as n goes up, the number of synapses goes up quadratically, right? So remember that we're then also going to evolve all of these edges, right? So the dimensionality of the search space that evolution is working over also goes up quadratically. So if we're going to try and evolve robots that are more and more complex, meaning n goes up, which means the number of synapses goes up quadratically, the problem for evolution is becoming harder quadratically. So what we would like to do is to allow evolution somehow to break the neural network into structural modules where there's a lot of connectivity within a module, but little or no connectivity between modules. That's structural modularity. Okay. Functional modularity, we saw this before when we saw the little humanoid robot that was shaking the block up and down and then left and right. Functional modularity is a little bit different. We might have a structurally non-modular network. Everything may be connected to everything else. I think I have a little cartoon of it here. So here's our network that is structurally non-modular. But remember that we had some neurons that changed their values slowly, and we had some neurons that changed their values quickly. And the slow neurons could push the fast neurons into different distinct patterns over time. You can view these little patterns as little modules. They're functional modules. Shake the block up and down, that's one module. Shake the block left and right, that's another module. It's a different way of thinking about modularity. This is actually a figure that came from that paper, and the alternative model they had for getting a robot to do these different motor primitives, these little simple tasks, one of the things they proposed is you could actually have a structurally modular network, 3 different little neural modules. Each one produced one of the desired motor primitives. And then on top, you have a 4th one here, which is this gate selection module, 4th little module here, which turns on and off the flow of one of these modules directly to the motors. So in this little cartoon here, this robot has 4 sort of little brains, if you like. The first 3 little brains are thinking about doing their task, whatever it is. They're always thinking that. The 4th one says, okay, you're allowed to control the body. Now stop, you're allowed to control the body, and so on. So I tried to use this figure from that paper to compare and contrast structural modularity with functional modularity. So far, so good? Okay, different ways of breaking down a problem. Okay, so you can probably guess where we're going with this. For a given task that we'd like our robot to do, how do we know what the modules should be? It's very non-intuitive to figure out how to break a task down into modules. So we could try. We could have the roboticist break the task down into several subtasks and assign different subnetworks, different structural modules to each of the subtasks. That would be one way to do it. Or we could get the evolutionary algorithm to not just optimize synaptic weights, but to decide which synapses exist and which do not. So the evolutionary algorithm could actually break a fully functional network into separate modules. Okay. However, it turns out, as you'll see in a moment, that roboticists and the robot, or actually this should probably be roboticist and evolution, may have different ideas about what counts as behaviors or subtasks. And here's a little cartoon to try and make this clear. This is yet another example of why thinking about thinking is misleading. Let's have a look at this little wheeled robot that we're looking at from above. Let's imagine that it has these 5 distance sensors on the front of its body. Let's imagine that this robot is going to be exposed to spheres and cubes in its environment, or cylinders and blocks. We're looking from above. We watch the robot just sort of move around at random for a while, and we notice, here's the robot driving past the cylinder, and here's the robot driving past the block. We might already be thinking about how to break this problem down into subtasks. The robot should do A when it drives past the cylinder, and it should do B when it drives past the block. So maybe we're going to try and hand design 2 neural modules. It should use this one when it's driving past a cylinder, and this one when it's driving past a block. We're already in trouble. Why? We can distinguish between them because we are looking from the distal perspective. Distal just meaning distant, right? We are looking at the robot, but we are seeing something very different from what the robot is seeing. The robot has a proximal perspective of its own behavior. Proximal meaning close to. Can't get any closer. It's actually in its own body experiencing its own behavior in real time. Right? So from our point of view, these 2 situations at these 2 points in time are different, and we might already start devising different things for the robot to do in that situation. But from the robot's point of view, here's my little cartoon of what the robot sees. It can't distinguish between these 2 situations. They're exactly the same. Now this is only a cartoon. When the robot starts to move at the next time instant, yes, it may be able to sense a difference between these situations. So this cartoon is just meant to illustrate a point, which is when we're thinking about a robot doing whatever we want it to do in its environment, we might have very different ideas about how to break that problem down into bite-sized chunks. But those bite-sized chunks might not be appropriate to what the robot senses when it is in that environment and it's performing those tasks. Make sense? Okay, and we're going to see this in a real experiment in a moment. Okay, so you might remember we introduced the Kepler robot way back at the beginning of the course. So this was one of actually the first experiments in the field. Very interesting paper from a conceptual point of view. So the research question they wanted to tackle was, how can we get evolution to break a problem down into manageable chunks for the robot? The task they set the robot was to pick up these little sugar cubes that they put in the robot's environment. And these sugar cubes, there are 5 of them placed inside of this arena. The robot had to drive around, find a sugar cube, grab it, pick it up, hold it up, drive to the edge of an arena, and drop it outside the arena. I think roboticists tend to be OCD. We always tend to focus on cleaning things up somehow. A lot of cleaning up tasks in robotics. Okay, so here's our Kepler. We've got 7 sensors, which are the 6 infrared sensors. These are the distance sensors. So again, like these beams that tell it distance from either sugar cubes or the wall, and a seventh sensor, which is a light barrier sensor. You can see this robot has its little claw here in front of it. So as it's driving around, if anything ever goes inside its gripper, there's a light beam from one pincer to the other pincer. And if that light beam is broken, that seventh sensor fires. When it drops an object or that object is no longer inside the gripper and the beam of light is unbroken, that sensor goes back to 0. So it can sense whether something is inside its gripper or not. 4 motor neurons, one which spins the left wheel, the second which spins the right wheel, and a third one which triggers this behavior, and a fourth one which triggers this behavior. So they kind of pre-program these motor primitives, these basic actions which are pick up and release. Sound good? Okay, 7 sensors, 4 motors. Okay, so the task again, pick up all the objects and drop them over the wall and thus out of the arena. So I've told you about the robot and the task environment. So let's, for fun, try and break this down ourselves. Here's one possible way you might start to decompose this problem. We could then go on to the next step, which is to create little neural modules that carry out each of these A, B, C, D, E, F, G, these 6 subtasks. So first one is if there's nothing inside your gripper, explore the environment but don't bump into walls. Drive around maybe at random, or if no sensors are firing, move forward. If the left sensor fires, turn right, and there should be A3 here, which is if right sensor fires, turn left. Does that remind you of any robot you've seen before? It's a Bradenberg vehicle, right? So if you're not holding anything, act like a Bradenberg vehicle, right? Drive around for a while. If you happen to recognize an object, move to the right position to be able to pick it up and then trigger the third motor neuron, which will pick up. Once you've picked up the object, steps 3, move towards a wall. Now avoid sugar cubes because you can't pick any more up. Recognize a wall, move close to it, and release the object. How is that? That's one possible decomposition of this task. Sound good? Why don't we just implement this in the robot and be done with it?
It doesn't really move. It doesn't really know where the sugar cubes are. It just kind of goes at random and hopes that it finds one.
Yes, so maybe it's not that efficient, right? Maybe we could actually try and get it to use its distance sensors to actively look for sugar cubes rather than drive around at random. It's also not immediately clear for these 6 subtasks, if we were to create 6 different neural modules for them, how big should those neural modules be? How complicated for the robot is it to, for step D, move towards a wall but avoid other obstacles, other objects while holding up the sugar cube? I don't know, it's not really that obvious to me. We might have actually decomposed this problem into not 6 simpler tasks, but maybe 3 simple tasks and 3 super hard tasks. We don't know, right? Because again, we have this distal perspective. We don't know what's easy and what's hard for the robot, given its sensors and given its motors.
It's also really inefficient because in the beginning steps, it knows it's avoiding walls, so it knows where walls are. But then we don't really tell it to remember that. Memory is an important step. And then when it has the object, it's avoiding sugar cubes, so it knows where the sugar cubes are. But when it drops it off, it again has to randomly do something, even though it knows where it is.
Exactly, right? So it's probably already seen a bunch of sugar cubes. Maybe we should have something in here about once you drop one off, remember where the last one was that you saw, turn 180 degrees and go back and get it, right? We could maybe make things a little bit more efficient, right? But even then, that might be a tricky thing to implement. This is, again, a non-intuitive thing for us to do, right? So again, you know where we're going with this. Instead of doing this manually, we're going to try and get evolution to break the problem into bite-sized chunks. And what we're going to be interested to see is if evolution does, what modules does it produce? And do those modules or those subtasks, they correspond to anything recognizable to us, right? Is evolution going to say, all right, robot is going to do this kind of thing when it's holding a sugar cube, and it's going to do this other kind of thing when it's not holding a sugar cube? That seems like kind of an obvious way to break this problem down from our point of view. Clearly, it should do different things whether it's holding a sugar cube or not, but that doesn't necessarily mean that evolution is going to find it equally intuitive. So let's see what evolution does. Okay. Before we build up to that, the investigators actually looked at 4 different neural networks. The 5th one, which we're going to see on the next slide, is a neural network that's designed in a way to enable evolution to break the task down into bite-sized chunks. Okay, but we're going to start with our simplest possible neural network, which we've seen many times before already. We've got our 7 sensors lined up here, and they're all connected. Each sensor is connected to each motor. So neural network A is feed forward, going from the sensors to the motors. No hidden neurons. Neural network B is exactly the same, except now we put in some hidden neurons. What is the advantage of putting in hidden neurons? What do hidden neurons do for a neural network? You remember all the way back to near the beginning of the course when we were introducing neural networks, and we saw a neural network that performed the OR task, the AND task, and then I asked you to design a neural network that performed the XOR task. We had to put hidden neurons into that one, right? There's no feed-forward network with no hidden neurons that can compute the XOR function. An XOR function is a nonlinear function, and an OR are linear. So the minute we put in hidden neurons, we enable the neural network to compute a nonlinear transformation from sensor values to motor values. Is a nonlinear transformation necessary for this task? Who knows? How will we know? We're going to evolve the robot a bunch of times with network A, and then we're going to evolve the robot again with network B. How are we going to know whether it was useful?
If B outperforms A.
If the robots do better at the task with B, then clearly for this task, given those sensors and those motors, it's helpful to evolve a nonlinear transformation from sensors to motors. Okay, we're still missing something in network B, of course, which is added in network C, which are recurrent connections. This is drawn in a way that you haven't seen before. We've got our 7 sensors here, or 7 sensor neurons here. We've got our 2 hidden neurons here. These 2 hidden neurons connect recurrently to these other 2 hidden neurons, which then project to the motors. And we have synapses that project directly from the sensors to the motors. So you can actually sort of redraw this network in a way that would be much more familiar to you, like this. Yeah. So B, we've added in hidden neurons. C, we've added in recurrent connections. And D, this is an interesting one. This is one in which the investigators have manually imposed some modularity. Here's module 1. And here's module 2. And you can see that in both modules, module 1 and module 2 end in 4 motor neurons. What does this mean? This means that a robot that's equipped with network D, at every time step, sensor values are arriving at the 7 sensor neurons. But which of the 2 modules is allowed to control the 4 motors is dictated by the 7th sensor neuron, which is whether the robot is holding a sugar cube or not. So the investigators have said, we're breaking this problem into 2 simpler pieces. The robot can do this when it's not holding a sugar cube, and the robot will do this when it is holding a sugar cube. So it's going to switch its behavior depending on whether it's holding the cube or not. And evolution, as always, is just evolving all of these synaptic weights in network D.
I don't know if this would be like a pointless step or not for the D, but
Yep.
Since one of the sensors is determining which modular motor setup to use, would it be more efficient to have all of the sensors go to one neuron and that one neuron would choose, instead of having all of the sensors go to every neuron?
So you're talking about an hourglass network. So we've got all our sensor neurons here.
Yeah.
They all feed down into one neuron here, and then this neuron projects to all of the motors.
Something like that, yeah.
Okay, it's a good idea. There's a problem with this, though. What's the problem? Let's say at some point in time, this sensor neuron has a value of 1, and this neuron has a value of 0. The next time step, this neuron has a value of 0, and this neuron has a value of 1. Let's imagine, actually, just to make this a little bit easier, let's imagine that these both have the same weights.
I was going to say, it would have a hard time reacting to different sensor information. It would just have to,
That's right.
that hourglass neuron would just have to tell the motors to do the same thing based off of different input.
Exactly. So you're losing some information in this compression at the waist of the hourglass, right? By making sure that every sensor can talk to every motor, you're giving evolution more flexibility in how to react given to what all the sensors are reporting. Okay, so far so good? Okay, now we get to the interesting one, network E. Network E takes a little bit to digest, so I'll go through this slowly. Okay, E is an emergent modular network. It's designed in a way that's going to allow evolution to dictate what the motors do in response to the sensors, but it's also going to allow evolution to sculpt different neural modules like this. How does this work? Well, let's start with the familiar part of the network. We've got our 7 sensor neurons down here. And we can see that there's 4 groupings at the top, which correspond to the 4 basic commands: left motor, right motor, pickup, and release. But each one of those 4 motor primitives has 4 neurons associated with it, instead of just 1. So why 4? Well, let's have a look at, first of all, the white neurons, which are called the output neurons. You can see that for each of the 4 motor primitives, there's a left and a right output neuron. And there are synapses flowing from every sensor to each of these output neurons. So they have their own synapses, which means these 2 neurons can light up with different values at the same time instant. You can think of these as 2 different things that the robot is considering doing with the left wheel. Neither of those 2 values has actually gone to the left wheel yet. It's sort of considering which of these 2 commands to send to the left wheel. The black selector neurons in the back there are going to determine which of these 2 values goes to the left motor. We've got 2 of these selector neurons back here. They also receive synapses from all of the sensors. So there are also 2 different values at every time step at each of these 2 selector neurons. If the value of the left selector neuron is greater than the value of the right selector neuron, the left output neuron sends its value to the left motor. If the right selector neuron is higher than the left selector neuron, then the value at the right output neuron goes to the left motor, right? So these selector neurons are kind of like a gate. They're allowing one or the other of the robot's 2 ideas about what to do with the left motor to flow actually to the left motor. Make sense? Okay. So we've got these, so we walked our way through this. So where are the modules in this? It's not strictly, this network is not structurally modular when you look at it, but it does have these structural modules. What are they? The easiest way to think about this is to compare this back to network D, right? Here are 2 different Here are two different ideas about what the robot should do at the next time step. And how does the robot determine which of these two ideas to actually carry through to reality? It's based on whether it's holding a cube or not. What determines whether this neuron controls the left motor or this neuron controls the left motor? Is it whether it's holding a sugar cube or not? Who knows, right? It's up to evolution. Evolution can sculpt these synapses to determine which of these two neurons, under which sensory conditions, control the left motor. Let's imagine that the seventh one here, which is the BL sensor, the light barrier sensor, whenever this is high, meaning the beam is broken, this goes through to the left motor. Imagine that when the light barrier is unbroken, this value is low, that this neuron takes control of the left motor. If we saw that in the synaptic weights, or we saw that switching between the left and right output neuron for the left wheel, then we would know that the robot is doing something different with its left wheel when it's holding or not holding a cube. As you can probably imagine from all this build-up, it's not as simple as that, right? It would be nice, but again, evolution does not always see the problem the same way we do. Okay, so another way to see the modularity in this network is to think about all the possible modules or states that exist. So I'm putting states in quotation marks here because really this is just one big continuous system. So we're going to define states as which of the two in a pair of selector neurons controls the motor neuron. So let's say state 0 is left is greater than right, left is greater than right, left is greater than right, and left is greater than right at state 0. State 1 is left is higher, left is higher, left is higher, and now right is higher. That's state 1. We've now switched to a different state. Suddenly there's a different part of the network that's controlling the release behavior. How many states in total are possible here? How many combinations of modules can the robot exhibit? A lot. Thousands, hundreds, dozens. How do we figure this out? Well, if we look at this pair, there's only two situations. Either left is greater than right, or right is greater than left. Let's ignore the slim probability that they're ever actually equal in value. So let's determine this as 0 when left is greater than right, and let's determine this as 1 when right is greater than left. So this can either be 0 or 1. Same thing here, same thing here, same thing here. So now state 0 is 0, 0, 0, 0, 0, 0. That's state 0. State 1 is 0, 0, 0, 1. State 2 is 0, 0, 1, 0, and so on. There's 16, right? So we're considering each of these pairs as taking on one of two binary values, 0 or 1. Left is greater than right, or the opposite, right? So there's 16 possible combinations of these modules. When we evolve these, do you think that the robot or evolution is going to take, is going to use all of these 16 states? Who knows, right? We're in very non-intuitive territory here. That's as much as it has available to us. Let's see what it actually does. Okay, so now we've got all 5 of our neural networks up here. We're going to, as I've already mentioned, we're going to do multiple evolutionary trials with each of these 5 networks, and we're going to look at the relative performance of the robot using these different networks. And if network B yields better performance than A, then we know that internal units or hidden neurons are useful. If C performs better than B and A, and we know that recurrent connections are useful. If that's the case, what does that tell us about this task or about the robot? If recurrent connections allow the robot to do a better job than the robot can do with A or B, what does that tell us about this task?
We should probably use some more recurrent connections.
Maybe more recurrent connections are useful, yes, that's one thing.
Nonlinear.
The internal neurons allow for this nonlinear transformation. So if the robots do better with B than they do with A, then that means that nonlinear transformations from sensor values to motors are useful. If the robots do even better with C than either with B or A, so if recurrent connections are useful, what does that tell us about the task?
Something that needs a little more
Memory, right? Remember that recurrent connections give us memory. So maybe when the robot drops a sugar cube outside the arena, it remembers where the last one is that it saw and turns at a certain angle to get back there, right? That's how we're inferring from different performances of the robot with these different networks. We're inferring indirectly what's useful for this task. Is nonlinear transformation from sensors to motors useful? Is memory useful? If D produces better behavior than C or B or A, then that means we were right. It makes sense to break this task into two separate subtasks. Do subtask A when you're holding the sugar cube, and do subtask B when you're not. Right? If D does not do better than C or B or A, that means we were wrong. That partitioning of the task into those two parts actually made things more difficult for the robot, not easier. If the robot does better with E than with the other four networks, that means modularity is useful, but we were wrong about what kind of modularity it is. The modularity we built into network D is not useful. There's some other modularity here that happens to be useful. Let's go back to this picture for a moment. Let's imagine that a robot evolves and does perfectly fine at the task. It picks up all the sugar cubes and drops them outside the arena, but there is never a switch between output neurons. Let's say in this network that succeeds, it only ever uses this neuron, this neuron, this neuron, and this neuron. The selector neurons behind never change their relative values. That would be evolution basically saying, thanks for the modularity, but I don't need it. I'm just going to do what I normally do. Actually, in that case, you would expect it did perfectly fine with network A, right? It doesn't need any modularity. Okay, you can again probably imagine from all this build-up that that's not going to be the case. Okay, I've held you in suspense for long enough. Let's have a look and see what happened. Let's start with the top figure. Looks pretty familiar. We've got evolutionary time on the horizontal axis and successful epochs on the vertical axis. What's an epoch? Well, when they evaluated each controller on the robot, they downloaded the controller onto the physical robot. So this was an early experiment from the 90s before physics engines existed. They put the controller into the robot, and then they put the robot at 15 different positions in the arena. And each of those is an epoch, and an epoch lasted for 200 actions, 200 updates of the neural network, or less actions if the robot during that epoch found a sugar cube, picked it up, got to the wall, and successfully dropped it on the far side of the wall. Okay, so what they're really mentioning is, or what they're actually measuring here, is not really fitness. They had a relatively complicated fitness function. They're just sort of showing how many successful epochs were there. How many times did the robot do the right thing in the arena? Okay, and then they evolved for 1,000 generations, and they did 10 replications. They did 10 evolutionary runs for each of the 5 neural networks. So you can see the relative performances of the robots with these 5 different neural networks in the top figure. What can you take away from this? What's the most obvious takeaway message here? Let's start with that.
Well, E was the best neural network.
E was the best at the beginning. Some of the others eventually caught up, but clearly the robots do better with E, which tells you what? Modularity is important, and the modularity we built in D is not the right one, right? So there's evidence that thinking about thinking is misleading. Imagine in a few years' time you go work for a robotics company, and that robotics company is going to build robots to look for human survivors at a disaster site. And your boss says, all right, you design the control software for this robot. The robot should do A when it's looking for a human survivor, and once it finds a human survivor, it should do B. Remember this lecture and remember this slide, and you'll know to say, I'm not so sure that that's really the way to break up this task.
This might be like the wrong way of phrasing it, but if you were doing this and you were to make this line for each neural network, like you make a neural network, make the graph, and you keep overlaying it.
Yep.
Once you switch from A to B, you would realize that making it nonlinear is drastically more efficient. What would be the jump to then say, let's make it modular and screw nonlinear anymore?
You're right, because in the modular case, it doesn't have the hidden neurons in there anymore. That's a good point. I think they just
dropped it for no reason.
I think they just missed it. So probably there's a network F, which is modular and contains hidden neurons, which I would predict would do better than all 5. That's a good catch, yes. What else can you learn from this? Is memory helpful? Memory was introduced in network C. Recurrent connections. Does that help? Yeah, somehow, right? Kind of useful. It's a little hard to see here. I'm pretty sure that the robot isn't remembering where the previous cube was and going back and getting it. Might be remembering something else, but that seems like a bit of a stretch.
Isn't C just pretty much A, but with memory? So if you just compared C and A.
C and A are not the same. C also contains hidden neurons.
That's the recurrent connection.
Recurrent connections within the hidden neurons, but A has no hidden neurons at all. Okay, so the lower plot is just a different way of looking at this. The successful individuals. So remember they did 10 replications of each of these 5 networks. And at the end of each of these replications, at the end of each of these evolutionary runs, they asked the question, did the best individual in the population, was it successful or not? So successful meaning, did it successfully clean the arena? Did it get all of the cubes out of the arena or not? I realize now that I misspoke. They did not do all of this work in the physical robot. They did it in a simulation. It was a 2D kinematic simulator, which is just a much simpler version of a physics engine. So they did do everything in simulation. They then took the best individual from each of the 10 replicates and each of the 5 neural networks. So they had a total of 50 evolutionary runs, 10 times 5. They took each of those 50 best controllers and dropped it into the physical robot and looked to see whether those 50 controllers successfully cleaned the arena or not. And we can see that E is the clear winner here, right? 7 out of 10 of those individuals, of those evolved individuals, successfully cleaned the arena. Okay, so you're probably now all dying to know how evolution did this. How did evolution break this task into simpler bite-sized chunks? Okay. First of all, let's ask the question, is there a correspondence between the evolved modules and distal behaviors? Again, meaning the difference between D and E, right? So distal behaviors meaning we decided, looking distally, that there should be 2 different behaviors when the robot is holding the cube or not. And we see that E blows D out of the water. So clearly there's not a correspondence between our decision about modularity and evolution's decision about modularity. So the answer to the first question is a resounding no. Let's have a look actually about what happened in one evolved controller E. So this is one of those 7 successful individuals. Only the right motor was controlled by both output neurons. What that means is that when this individual was driving around in the physical robot, there was a switch between these 2 selector neurons. At one point, one was higher than the other, and at the next point in time, the other one was higher than the other, which means this was controlling the right motor for a while, then this one was, then this one, then this one, then this one. And in the other 3 motor neurons, in the other 3 groups, one of the selector neurons always won, which means there was never a switch between these pairs of output neurons. So evolution, like us in D, said, I only need 2 modules. I'm going to do this when I'm in one module, and at a certain point in time, when I sense something else, and we haven't said yet what that something else is, I'm going to switch and do something else with the right motor. So there is this switching between modules, but it's clearly not the 2 modules that we had previously determined. Okay, take a deep breath. We're going to try and now figure out exactly what these 2 situations are. This takes a little bit of parsing again. So let's start with the easy part in the top left here. So you'll notice in this case there were 5 sugar cubes inside the arena, which correspond to the 5 circles here. The white circles are sugar cubes that were successfully picked up by the robot and dropped outside the arena. The robot failed to see, well, we don't know if it failed to see, it failed to clean up those 2 other sugar cubes. The line here shows the trajectory of the robot, so here's where the robot started moving. And if you look very carefully and you follow this line, you can build up in your head an animation of how this robot actually did what it did. It's not too important for our purposes. Okay, so here we go. Let's work our way down this figure starting with the top row here. So mod is module, which indicates which of the 2 modules controlled the right motor. Remember that we just saw that this module controlled the right motor for some of the time, and this module controlled the right motor for the rest of the time. So the horizontal axis here is the time during which the robot was moving in the environment. So this is not evolutionary time now. This is the lifetime of the robot. So it starts in module 0, and it doesn't really matter whether that's the left output neuron going to the right motor or the right output neuron going to the right motor. It's one of them. Whichever, left or right, doesn't matter. Left, 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 right, 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 left, right, left, right. You can see it switching back and forth between these 2 modules over its lifetime. Before we go any further, what can you tell me about how it's using these 2 modules? I've already told you that these 2 modules don't correspond to use one module when you're holding a cube and use the other module when you're not holding a cube. I already told you that. But you can actually tell already by looking at this picture, by looking actually just at this row. How can you tell just by looking at this row that it's not doing that?
It didn't pick something up however many times there's a line switch.
Exactly, right? So if it was, then it would be sort of picking up and dropping the object very, very quickly, which it's definitely not doing, right? If it was using one module while I was holding the cube, you would expect to see a continuous black bar in that top row, and then when it drops it and goes looking for another cube, you would expect to see a continuous expanse of white, finds another module, finds another cube, picks it up, another block of black, block of white, block of black, and so on. So it's not continuous spans of time in which it's using one or two of these modules. It's switching back and forth between them very rapidly, which is a little depressing because we know as we move on now it's going to get harder to figure out what these two modules correspond to. Let's see if we can figure it out. So as we go now, we're going to look at each of these rows and compare it visually back to this row. Right? Can we see any pattern, any correlation between what's going on down here and what's going on up here? Let's start with WT. So WT is what is perceived. So is it actually facing a wall or is it facing a target object? So here it's facing the wall, or sorry, here it's facing target, target, target. Here it's facing the wall. Here it's turning and it doesn't see anything, sees a wall, doesn't see anything, sees a target object, probably holding the target object, looking at it for this period, and so on. So do these two modules correspond to whether it's looking at a wall or looking at a sugar cube? No way, right? There's no correspondence between this pattern and this pattern. Here's what the left motor is doing. So this is when there's a black bar here, that's the left motor spinning quickly. And when there's white in here, that's the left motor spinning slowly or not at all. Is there a correspondence here? Some. Kind of. This is already confusing now, right? So we know that the module is switching control of the control of the right wheel. It's the module switching is not affecting the left motor at all, but the left motor seems to be moving in lockstep, more or less lockstep with the switching. So what's going on here?
Looks like the robot likes to drive straight a lot.
How do you know How do you know from these two pictures whether it's driving straight?
Just because, like, not always straight, but they're relatively the same color around the same time.
That's it, right? So wherever there's black in both of these pictures, both wheels are spinning fast, which means it's more or less going straight, right? When one is white and the other is black, it's turning left. When one is black and the other one is white, it's turning right, vice versa. Okay, so some correspondence here. Definitely correspondence with the right motor, which makes sense because the module is switching which of those two output neurons controls the right motor. The reason why there may be a correspondence between the left motor and the module is because remember that the module switches what the right motor is doing. Let's imagine that the right motor suddenly goes from moving quickly to moving slowly. So suddenly the robot's motion changes. And because this is an embodied agent, remember this is one of the unavoidable consequences of being an embodied agent. The moment you suddenly change how you're moving, what else changes? What you perceive, right? So suddenly the sensor values might change. The sensor values are flowing up the synapses to the left motor. Suddenly the left motor also does something different. Right? So things are propagating from the right motor to the environment, back to the sensors, out to the left motor.
Are these both or all of these on the same time scale?
They're all on exactly the same time scale. They're measuring all of these variables at each tick of the clock as the robot was cleaning this environment.
So we just like launched the cube over the wall. It didn't stop. The robot didn't stop once it put the cube over the wall. It just like pelted it and then.
It certainly didn't spend a lot of time stopped, right? So yes, you're right. It drove up to the wall, and however it did it, it dropped the cube out pretty quickly and then got the heck out of there to go try and find another one. Right? Makes sense. You're not likely to pick up any fitness points if you're just standing around doing nothing. Okay, let's keep going. So here's pickup and here's release. You can now see when it picked up each of the three cubes, right? So release means, let's start with pickup. So pickup means it's going along and pickup is not being triggered. At some point, it is triggered and you see these little spikes here, which is it doing this, right? And eventually picking up. Release is release is triggered in this, release is inhibited during this period, right? Don't release the cube. So here it is holding and transporting cube number 1, drops it, goes looking for another one, finds a second cube, picks it up, transports it, throws it outside the arena, goes looking, finds the third one, picks it up, travels to some wall, and drops it outside the wall. Any correspondence between these and the module? Not at all, right? So if we were right, we would expect to see a correspondence between these guys and this guy, right? Do something when you're holding the cube, do something else when you're not, right? That's clearly not happening. Okay, so let's keep looking. These didn't correspond that well. There's some correspondence, but not perfect. Here are these 6 infrared sensors. Is there some correspondence here? Some. It's not perfect, right? And it's not quite what we have in mind. What do these mean here? What do these bars mean? What's that?
Receiving input.
It's receiving input, yeah, from what? Let's actually look at this point in time here. What do you think these infrared values are, sensor values are denoting? What is the robot seeing at this time?
The wall.
It's the wall, right? We know that it has the sugar cube here, and it's not really seeing anything. So it's holding the sugar cube up like this and driving around, gets to the wall, and suddenly drops the cube, right? And it sees the wall for this period here, so maybe it's turning or doing something, and then finally turns away from the wall, drives off. And what about this one here? What is it seeing here? It's seeing the sugar cube, right? This is the point in which it picks up the second sugar cube, and it's exactly the same point where some of the infrared sensors light up. So it kind of looks like here, at least, when it's seeing the wall, that it's using module 1 more of the time than module 0. So maybe this modularity corresponds to do something when you're stuck next to a wall. Hard to say. Here's the light barrier sensor. So you can see that LB correlates or is inversely correlated with RL. Why? What does this mean, and why does this make sense for the robot?
What's the light sensor that's going through?
This is the light sensor, right? So here the light beam between the pincers is unbroken. There's nothing between the pincers. Suddenly the beam is broken by a sugar cube, right? And what happens to release?
It turns off but
It turns off, right? Release is inhibited, and pickup spikes, right? So suddenly the light beam is broken, pick up, and release is inhibited. Don't drop it, right? It's holding it, and then finally release is released, and it releases the sugar cube. Did you have a question?
No, I was going to say you can tell that it didn't drop the sugar cube.
Okay,
Like that.
right, you can see that too. And the following 1, 2, 3, 4, 5, 6, 7, 8 down here are periods in time in which the robot was doing some subtask that was obvious to the investigators. So the investigators were watching the robot. They said, in A, it's not carrying the object. It's carrying object. It's not A. It's not carrying the object. It's not looking for a wall. Now it is carrying the object and it's looking for a wall. These are all distal explanations of what the robot is doing. Either it is doing A or it's not. It is doing C or it's not. Do any of these correlate with the module up here?
C seems like it's really close.
C is maybe, not quite. Some correlation. So in all of these, there is some overlap, but not perfect, which means, unfortunately, it's impossible for us to say what the robot is sensing when it decides to switch between these. we could actually measure those sensor values and say, okay, when infrared is between 0.2 and 0.3 and infrared 2 is between 0.1 and 0.9, then it uses module 0, otherwise module 1, but that doesn't mean much to us. So this plot is interesting because it shows that it's useful, like for humans, to break problems down into simpler subtasks, but that it breaks, in this task at least, it breaks things down into subtasks very differently from how we might have done so. Okay, I think we're out of time, so we'll finish lecture 13 on Thursday. You have a quiz due tonight, and undergraduates, you're working on assignment 9. See you on Thursday.